Okay, so this video is going to show you how to do a couple derivatives using the power rule. And recall that the power rule is if we're given a function, let's call it f of x, and it's some number times x to a power n, then the derivative of that function, or f prime of that function, would just be the product of the coefficient and the power, so a times n in this case, times x to the power of whatever n was minus 1. So let's look at a few examples to see how that works. Of course, if the function's y, we'll denote the derivative by dy dx. And I'll take 5 times 4 to give me 20, and then x to the n minus 1, so 5 minus 1, which is just 4. And that's it. 20x to the fourth. Here, if I want to find the derivative, it's f prime of x, same as below. Although the exponent for x is hidden here, so we know that it's a 1. 1 times 7 is just 7, and then x goes to the 0 power. But x to the 0 power, just like anything to the 0 power, is just 1. So this is really just 7. And since we know that the derivative is the slope, this makes a lot of sense because this is a line and the slope of this line is 7. So since the slope is the derivative, it makes sense that the derivative there is 7. Likewise, if we look at this, if we interpret number 3 as a line, it's going to be a horizontal line with a slope of 0. And when we go to calculate the derivative, we're going to notice that it is in fact 0. If you're wondering how we got there, you could think of y as 3 times x to the 0. And then anything, if we use our power rule, anything times 0 is 0, so I get 0x to the negative 1 for my derivative, which is still just 0. This is actually true no matter what the constant is. So if I have y equals b, where b is any constant, then the derivative dy dx is always equal to 0. It doesn't matter what the number is, it's always going to be equal to 0 for the derivative because they're all just horizontal lines. So if we look at some other examples here, these are a little more complicated, but really it's just the same thing over and over again. G prime of x is just going to be 3 times 5, or 15x to the 3 minus 1 squared, plus 4x minus 4. Notice each one of those worked just the same as our other examples, but when we have them in succession, when we have multiple terms, we just apply the power rule each time. Likewise, over here, dy dx. Well, you might have noticed that I got a little ahead of myself because it's not written in the same form. I need to use the distributive property first. So I can rewrite this as 12x minus 3x cubed, and then my derivative would just be 12 minus 9x squared. Often you'll see them written in descending orders of the power of x, so you might see it written as negative 9x squared plus 12, but either one of those is an acceptable answer for the derivative of this function. And if we want to look at a couple more complex examples, we can do that. So consider the function where y equals 3 over x squared plus 5x cubed. Now I'm going to rewrite this one before differentiating, just like we did in the last one, as 3x to the negative 2. We know how to do that from working with our negative exponents, plus 5x cubed. And then you'll see we're just going to use the power rule once again, negative 2 times 3. But this is where we have to be a little tricky with our negative signs. 3 times negative 2 gives me negative 6. And when I subtract 1, this doesn't go to negative 1 like some students often mistake. Negative 2 minus 1 is just negative 3. And then I can say plus 15x squared. Now, if the problem was originally given with x in the denominator like this, often the answer will be given with x in the denominator as well. So you might see this rewritten as negative 6 over x cubed, where the exponent is now positive, plus 15x squared.